So we're going to start off with going backwards in time to a long time ago when we learned what the product rule is. So the derivative of u times v, right? I'm just going to write that down here. The derivative with respect to x of one function u times another function v is the product rule. And what does the product rule say? It says that it's the first function times the derivative of the second plus the second times the derivative of the first. Everybody agree with that? That's our product rule, u dv plus v du.
Agreed.
Okay. So what I'm then going to do is I'm going to take both sides of this, and I'm just going to add in some dx's to everything here. So I'm going to rewrite this as let's see, I'm just going to put a dx there, and I'm going to put a dx here, and I'm going to put a dx here, which should seem like that's okay, right? I mean, I'm just multiplying every piece of this by dx. That's a legal thing to do, right? In math, you can multiply everything on both sides of an equation by the same term. True? Yeah, true. Good responding. Now what we're going to do is we are going to integrate both sides of this, which seems kind of stupid because we just took the derivative of both sides of it. Why would we want to integrate both sides of it? Well, because we do. So what's the integral of the derivative of some function u times v dx?
uv.
It should just be uv, right? It should just be that original function u times v. What about the rest of this? Let's u dv dx is, if we're integrating this, all that's going to happen is, effectively nothing, right? I can't integrate u if it's in terms of v or in terms of x. This is just the integral of u dv dx. And this is the same issue. I can't integrate this because I have v's and u's in here when I'm supposed to be integrating in terms of x. And so what we're going to do here now is we're just going to rearrange this so that we end up with this integral of u dv on one side by itself. And we should then be able to say that that's equal to u times v minus the integral of v du. And I'm dropping the dx's on there and are off of there, and there's a reason why I'm dropping them off of there. It's because each of these functions in here, dv and du, are going to be written in terms of x, and they are going to have a dx term attached to them already. So we don't need to just be redundant and have the extra one there. So what this is telling me is if I can take two functions, if I have some function that is a product of two functions where one of them is a function and the other could be written as the derivative of some other function, well, that integral is equal to u times v minus the integral of v du, which doesn't sound like it's really that important of a thing, but it is. This is a formula that is called the integration by parts formula, and it just obviously comes from the product rule and just doing the product rule in reverse with some integrals. And this is going to be the first of many new techniques that we're going to use to integrate some functions this year. So it's going to seem a little bit confusing at first, but does everybody agree that we could go from here all the way down to here just by following this series of steps to get that formula?
Yes.
Okay, great. So then we're going to use that formula to integrate some functions that we previously would not have been able to integrate. So I put the formula up here. Integral of u dv equals uv minus the integral of v du. Integration by parts, and you need to memorize that formula and be able to apply it to functions like this one, x sine x dx, that we want to integrate. And so if we were trying to think about this before we knew how to do integration by parts, x sine x dx, well, it's a product of two functions, and there's no u substitution, I don't think, that you would see right off the bat that you could use for this. I mean, nobody sees a u substitution there, I assume. True? To integrate that?
True.
Yeah, if you do, then you're either delusional or inspirational. I don't know, because there isn't one, and you've somehow come up with something that will work. So what we need to do then is we need to treat this thing in here as, you know, I should just circle the integral, this thing inside my integral, as if it is a u and a dv. So I have to break what's up inside the integral into two separate functions, one that is u and one that is dv, the derivative of some other function v. And I need to be able to integrate that other function v, because I need to be able to plug in some just regular old v's into my integration by parts formula. So I'm going to give you a basic rule for how to break this up. Generally, whenever we do an integration by parts, you're going to want the dv term to be the most complicated thing within here that you can still take an integral of fairly easily. Okay. So what's the more complicated piece of x sine x that you can still take an integral of?
Sine x.
Sine x. So we're going to let u equal x, and then we're going to say that dv is equal to the rest of it, which is sine x dx. And so now you can probably see how that dv is getting the dx attached to it, because we're taking the integral originally of something that's all in terms of x. All right. So would you all agree now that this integral, the integral of x sine x dx, is now written in a form where it is the integral of u dv?
Yes.
Yeah.
Okay. So what's du then? Because we're going to need to put a du in.
1.
1
dx.
dx. Yeah. And what is v equal to?
Negative cosine x.
Yeah, the integral of sine x is negative cosine x. So v is just negative cosine x. And so now all we have to do is say that this integral is equal, using the integration by parts formula, to u times v, which is negative x cosine x, minus the integral of v du. And du is dx, so I'll just replace the du with a dx. Everybody good with that? So far? Okay, great. And so then all we have to do is integrate. If we wanted to, we could turn that into plus an integral of cosine x dx first, just taking the negative out. And what does that give us? Negative x cosine x
Plus sine x.
plus sine x plus your constant. And so that ought to be the integral of x sine x dx, using integration by parts. And if we wanted to check our work on this, we could just real quickly go in and take the derivative of what we got, negative x cosine x plus sine x, plus c, I guess, if we want. And that should give us negative x times the derivative of cosine, which is negative sine. And then plus the derivative of negative x, which is negative 1 times cosine. And then plus the derivative of sine x, which is cosine x, and then plus 0. And we'd see those negatives would cancel out. It gives us x sine x, and the minus cosine and the plus cosine cancel out. And so we're right back where we started with x sine x as the derivative of negative x cosine x plus sine x. Good or no?
Good.
Anybody have any questions on that? No? All right, let's try to do another one. Natural log of x dx. Any thoughts on what we can do with this?
Could we exponentiate it?
We could exponentiate it, I suppose we could try to, but we don't want to do that.
Do we assume dv is dx?
Sorry, say that again?
Do we assume dv is dx?
Yeah, so we're going to have to make dv equal to dx because the only other piece of this function that we have is natural log of x. And if I tried to make dv natural log of x, well, to find v, I'd have to integrate natural log of x, which is what I'm trying to do in the first place. And I don't know how to do that. Well, I do, but we don't know what that is yet. So we're going to separate this out into u is natural log x and dv is dx. Everybody okay with that?
Yeah.
All right, so what should du be?
dx over x.
Yeah, it should just, well, I'm just gonna, dx over x is fine, or 1 over x dx. Okay. And then what should v be when we integrate both sides of this? V should just be
X.
X.
good. So now as we put this into our formula for integration by parts, what should it look like? Should be u times v, which is x natural log of x minus x natural log of x minus the integral of what? Should be
X
v
over x.
du, right? So x times 1 over x dx, or we end up with x ln x minus the integral of 1 dx, which is just x ln x minus what's the integral of dx?
X.
X, so minus x plus our constant. Good or no? Any
Yeah,
questions on that? That's okay. Everyone's all right with that? All right. Cool. Let's try another one. We got t squared e to the t that we want to integrate. Any thoughts on what should be u and what should be dv? What's the most complicated?
More complicated one, right?
Sorry, say that again.
B was supposed to be more complicated, or like
The dv should be the more complicated thing that we are easily able to integrate.
t squared.
For u or for dv?
Or for dv, sorry. Well, because the e to the t is just et, right?
Right, but e to the t is a more complicated function than t squared, I would argue. So I'm going to add another little piece to this, that if we're going to make dv e to the t, if you can differentiate the other thing so that it goes down to become 0, about 99.9% of the time you will want that thing to be your u. So if you just have a polynomial as one of the two functions, generally make that polynomial your u. Okay. So what should du be?
Wait, shouldn't there be a dt on one of those two?
Oh, sorry, yeah, dt on my dt. So what should my du be?
2t dt.
2t dt, and what should my v be?
E to the t.
Just e to the t. And so now the integral of this should be u times v, which is t squared e to the t minus the integral of v du. So minus the integral of 2t e to the t dt. Good or no? Everybody okay with that so far?
Yeah.
Okay. So now with 2t e to the t dt, there's still not a good simple u substitution to use there. And so it looks like, what are we going to have to do, you think?
Another integration by parts, possibly.
Another integration by parts. So what will u be?
2t.
2t, and dv will be e to the t dt again. Du will just be what now?
2.
2
2 dt.
and v will still just be e to the t. And so the second application of integration by parts gives us t squared e to the t minus, and I'm going to put my new integration by parts things into parentheses or brackets here, whatever. So uv 2t e to the t minus the integral of v du, which is 2e to the t dt. Good or no? So we got t squared e to the t minus 2t e to the t, and then this minus gets distributed to this minus, which makes it a plus. And what's the integral of 2e to the t?
2e to the t.
Plus 2e to the t plus a constant. Good or no?
Yeah, that's really cool.
That's pretty cool. So sometimes we may have to apply integration by parts more than once. Up to 2, 3, 4, 5, 25 times. Who knows how many times? Conceptually, everybody good?
What would you do if you ended up with more than two functions inside the integrand? So if that's a word.
That is a word. Yeah, if you had more than two functions inside of there,
Yeah, so you couldn't pick it.
yeah, so you'd have to try and break it up so that you wrote one function, either your u or your dv was two of the functions together, and then the other one was the third function. But you'd have to, for example, if you had your u be two of the functions multiplied, well, then you'd have to use the product rule for your du. Or if your dv was two functions multiplied together, you'd probably have to integrate it using like a u substitution to get your v value. But it's possible that that could happen.
Okay.
All right. Any other questions before we go on to the next one? No? All right. The integral of e to the x sine x. So which of those is more complicated?
Sine x.
You think sine x? Okay, sure. It's kind of hard to say, I would say, with those, but you want to make dv sine x then, I assume? So u would be e to the x. Because we could integrate either one of those, right? And we could also differentiate either one of those. So maybe it doesn't matter which way we go this time. What is du?
E to the x dx.
E to the x dx. And what is v?
Cosine x.
No.
Negative cosine x.
Negative cosine x.
Oh,
Okay.
right.
Yeah. So we've now got this equals what? Negative e to the x cosine x, right? U times v, negative e to the x cosine x. And then minus our integral of v du, which is minus the integral of negative cosine x e to the x. So could I throw the negative out there and just make that a plus? And then have this be e to the x cosine x dx. Everybody good with that? Or no?
Yeah.
Yeah, okay. Well, what's the problem that we've got here now? We've got an e to the x cosine x dx inside my integral, which is very similar to what I started with, right? And it's going to require us to use what?
Integration by part.
Integration by parts to deal with it. So
Wouldn't this repeat infinitely with the cosine x?
well, let's see what happens. Let's not get ahead of ourselves. U equals e to the x, and dv would be cosine x dx. And du will be e to the x dx, and v will be what? Sine x, right? If I remember how to integrate correctly. So what do we have? We have negative e to the x cosine x, what we had already, plus u times v, which is e to the x sine x, minus the integral of v du, which is e to the x sine x dx. And so Derek, that was you talking, right? About this is just going to repeat infinitely, blah, 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 right?
Yeah.
Yeah, I mean, it sure seems like it has, right? It's gone right back to e to the x sine x dx, which is the integral we were trying to find in the first place. So that seems to be a bit of a problem, doesn't it? Because if I try to integrate by parts again, right, if u is e to the x and dv is now sine x dx again, I'm just going to get that same thing again and then do it again and get the same thing again. So how can I get us out of this sort of infinite loop of death that we're looking at here?
You can't. Death is inevitable.
Okay. So that's not helpful. How can we get out of this infinite loop?
You set what you have now equal to your original integral, and then you can solve for the integral.
That is exactly right. Who was that talking?
Denise.
Ah, that's what I thought. Okay. Good job. So this is equal to the integral of e to the x sine x dx, isn't it? Isn't that what we started with? We said this was equal to this, which was equal to this. So that, this big long integral that we got with another integral in it should be equal to what we originally started with. And so now we can get out of this infinite loop that Derek found for us by adding this integral over here and saying that negative e to the x cosine x plus e to the x sine x equals 2 integrals of e to the x sine x dx. Everybody good with that? And so what does the integral of e to the x sine x look like? Should be negative e to the x cosine x plus e to the x sine x all over 2 plus the constant. Good or no? It is pretty amazing, isn't it, Shri?
Yes.
Yeah. Everybody good there? Anybody have any issues with that? So we'll note that if we end up in this infinite loop here, where we're just going to go back to what we started with, once you get back to what you started with, set it equal to your original integral, and then solve for that integral as if it was just a variable. Are you all good or no? You're all very quiet, so everyone's good?
Glorious.
All right. Let's tackle another little integral here. Natural log of x squared dx. Any thoughts on this one?
U sub?
U sub. What do you want to U sub out?
ln x, because it's a composite, or it's like two functions in one. So
So you want to make it u squared?
I think
So then what's
so.
your du going to be? Your du is going to be 1 over x dx?
Yeah, and then what is that the correct answer?
No, it's not. I mean, that would give you u squared dx, but if u is natural log x, du would be 1 over x dx, which means that I'd have to put a 1 over x in here, which means I'd also have to add an x in there, and then I'm going to have to add in, you know, e to the u into this, and then it's going to be, I mean, we could do this, but it's a lot of substitution to just get something else that we're going to have to integrate by parts a few times. So it looks like it would work out, but it might take us longer than we'd like. I want to just go straight to integration by parts. So I'm looking here. It's like Ryan said, make a u natural log x and dv equal natural log x. I guess we can try that. Everybody okay with trying that? Or no? Okay, cool. All right, so du is
1 over x dx.
okay, and v should be, what's the integral of natural log of x? Well, we found that a couple pages ago, right? That's x ln x minus x. And it's quite possible that when we did that slide, I didn't mention to you, I'm going to go back to it real quick, that you should memorize that and know that the integral of natural log is x ln x minus x. Okay, so if you don't know that and don't have that memorized, memorize that one. That one comes up very often. It's good to know. All right, so this integral becomes the u times v. That's kind of a pain. Natural log of x times x ln x minus x. Okay, uv minus the integral of v du. So 1 over x times x ln x minus x dx. Good or no?
Yep.
All right. If I distribute this all clear, that's x natural log squared of x minus x ln x, and then minus what integral here? This just becomes minus an integral of what? Ln x
X minus 1.
minus 1 dx. And so that gives us x ln squared x minus x ln x minus the integral of all of this. What's the integral of ln x? It's x ln x minus x. And then the integral of minus 1 is minus x plus a constant. Everybody agree with all that? And what do we get? X ln squared x minus an x ln x minus another x ln x is minus 2x ln x's. And then minus x and a minus x is minus 2x. But if I subtract that, that's a plus 2x plus our constant. Good or no?
Delicious.
All right. Let's take a look at another one. Everyone okay with that one?
Yes.
All right. E to the 2x sine 3x. Any thoughts on this one? What do you want u to be?
E to the 2x.
Okay. What do you want dv to be then? I assume sine
3x dx.
dx. So what's du? Du ought to be 2e to the 2x dx. And what should v be?
Negative 1/3 cosine 3x.
Negative 1/3 cosine 3x. Exactly. And so that's why I was saying you really want to be able to do the simple u substitution integrals without having to write them out, because otherwise it's a pain to have to do a u substitution to figure out what v is when dv is sine 3x. You should hopefully just know that that's negative 1/3 cosine 3x. So this integral is equal to u times v, negative 1/3 e to the 2x cosine 3x minus the integral of v du, so that'd be minus 2/3 e to the 2x cosine 3x dx. Good or no?
Fun.
And this constant can be pulled out to make that a plus 2/3 times the entire integral. And what are we going to have to do? We're going to have to do another integration by parts with u equal to e to the 2x, where du is still 2e to the 2x. I'm not sure why I made this look like this, but we'll fix that. And dv will be cosine 3x dx, which tells us that v is equal to 1/3 sine 3x. Good or no? Everyone good or no?
Yeah, that's good.
All right. So now we have negative 1/3 e to the 2x cosine 3x, and we pulled that minus 2/3 out, so this is plus 2/3 times our new u times v, which is 1/3 e to the 2x sine 3x, and then minus our integral of v du, which is minus 2/3 e to the 2x sine 3x dx. Good? Or no?
Good.
And we'll note that what do we got here? We've got, again, an e to the 2x sine 3x, which is what we started with. And so as soon as we get back to what we started with, we're going to want to say this is equal to our original integral, the integral of e to the 2x sine 3x dx, and then solve for that integral. So what do we have here? We've got negative 1/3 e to the 2x cosine 3x plus 2/9 e to the 2x sine 3x. And then here we're going to have a minus 4/9 of this integral. So if I add a minus 4/9, if I add that to the other side, that's going to be plus 4/9. So if I have one of those integrals and I add 4/9 of that integral, that should become equals what?
13/9 of that integral.
13/9 of the integral of e to the 2x sine 3x dx. Good or no? And so the integral of e to the 2x sine 3x dx, I just got to multiply this by 9 and divide by 13. So I'm clearly going to have an over 13, right? If I multiply by 9, this one's going to become negative 3 e to the 2x cosine 3x. And this one's just going to become a plus 2 e to the 2x sine 3x all over 13 plus our constant. Good or no?
Fun.
I don't know what happened to the rest of that line. There we go. Anybody have any questions, any issues, any problems with any of that? All right. Let's do a definite integral here. The integral from 0 to 1 of inverse tangent x. In fact, actually, before we do this, just for, we'll do it afterwards. All right, let's find the definite integral from 0 to 1 of inverse tangent x. So what's the most complicated thing in there that you already know the integral of?
Inverse tan of x.
You know the integral of that?
Dx, right?
Yeah, so I mean, do we know the integral of inverse tangent x already? We don't, right? If we knew it, we'd just integrate this. But since we don't, we got to make the dv our dx and the u our inverse tangent x. Everybody good on why we got to make u inverse tangent and dv dx? Hopefully. Yes, no, maybe.
Yep.
Okay. So if dv is dx, what is v?
X.
That's right, Max. My 7-year-old shouted that out before all of you. And what's our du going to be? It should be 1 over 1 plus x squared dx. Yeah.
Yeah.
Okay. So this integral should be u times v x inverse tangent x minus the integral of what? V du, x over 1 plus x squared dx. And what do we have to do with the things inside of here? This one's got to be evaluated from 0 to 1. And this has got to be it's got to have limits from 0 to 1 for the integral, right? Because this is our original definite integral from 0 to 1. Good or no?
Yes.
All right. So let's do the first part of it. X inverse tangent x from 1 to 0. Well, that's just 1 times the inverse tangent of 1 minus 0 times the inverse tangent of 0. And then we have minus this integral. And how am I going to do the integral of x over 1 plus x squared?
U substitution for 1 plus x squared.
All right, so we're going to get rid of all this. We're going to let u equal 1 plus x squared. So du will be 2x dx, which I have an x, so I need to put in a 2, and I need to put a 1/2 outside. So effectively, this becomes minus 1/2 the integral of 2x dx is du over 1 plus x squared, which is u. And our limits have to go, instead of 0, u will be 1. And instead of 1, u will be 2. Good or no?
Yes, good.
All right, what's the inverse tangent of 1?
Pi over 4.
Okay, so we got pi over 4 minus 0. So minus 1/2 natural log absolute value u from 1 to 2, which ought to give us pi over 4 minus 1/2 natural log 2 minus natural log 1. Natural log of 1 is 0, so we just end up with pi over 4 minus 1/2 natural log 2. So the area underneath the curve inverse tangent x from 0 to 1 is pi over 4 minus 1/2 the natural log of 2 units squared. Good or no?
Extraordinary.
Should we
Yeah.
memorize this one too?
Yeah, this is a good one to know for inverse tangent, which is what I was going to say. Let's go in. This is what I was thinking about doing beforehand. But if we want to just find the integral of inverse tangent x, the indefinite integral, right? U would still be inverse tangent x, and dv would still be dx, and du would still be 1 over 1 plus x squared dx, and v would still be x. And we would have ended up with x inverse tangent x minus our integral, and we had x over 1 plus x squared, right? And we needed to put in the 2 and the 1/2. And then we did our u substitution, so this became x inverse tangent x minus 1/2 natural log absolute value of u. And what was our u? Our u was absolute value of 1 plus x squared plus our constant. And then we would note that 1 plus x squared is always positive. So this is x inverse tangent x minus 1/2 natural log of 1 plus x squared plus our constant. And yeah, I mean, that's probably a decent one to know. It's helpful to just sort of know that. It doesn't come up as often, but sure, good one to know. But if you forget, you can always do it using integration by parts. So good or no?
Spectacular.
All right. Does anybody have any questions on integration by parts in general so far?
So to summarize, you just have to keep integrating by parts until you don't get a function times a function, or you find something that you can integrate using U substitution.
Correct.
Okay.
Yep. All right. Let's take a look here at x cubed e to the x. X cubed e to the x. It's similar to, we did like t squared e to the t earlier, right? X cubed e to the x dx is very similar to that. What do you think your U substitution should be?
U is x cubed, and then e to the x is dv.
Oops. Okay. Which will give you du is 3x squared dx, and v is e to the x. Which ought to give us x cubed e to the x minus the integral of 3x squared e to the x dx. And what should we do with that? We should integrate by parts, where u is 3x squared and dv is e to the x dx. So du is 6x dx and v is e to the x. Minus our entire, this time, u, v minus the integral of v du. And what do you think we need to do one more time here?
One more integration by parts.
One more integration by parts. This time u will be 6x, dv will still be e to the x dx, du will be 6 dx, and v will be e to the x. So x cubed e to the x minus 3x squared e to the x, and then plus u times v, 6x e to the x, minus the integral of 6 e to the x dx. Which will then give us x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus a constant. Everybody good with that?
Yes.
All right. So let's take a quick second and analyze what happened here. When we repeatedly did integration by parts, the first term was our original thing that we were trying to integrate, wasn't it?
Yeah.
X cubed e to the x. Our second term was the opposite of the derivative, right, of our first du times our first integration, right, which was e to the x. Then we had switched back to a positive sign, and we had the next derivative and the next integral, again, e to the x. Then we switched signs again and went to the next derivative and the next integral until we got down to just a constant times our original dv. Everybody see that?
Yeah.
Each one of these, x cubed minus 3x squared, 6x minus 6, is the opposite of the derivative of the previous one, right? Derivative of x cubed is positive 3x squared, we got a negative. Derivative of that is negative 6x, we got a positive. Derivative of 6x is 6, we got a negative. Derivative of 6 is 0, right? So if I were to continue the pattern, the next one would be 0 times e to the x, which would just be 0, right? Which is why we stop at this 6 e to the x. And so there's this really cool pattern that forms anytime you have a integration by parts where one of the terms can differentiate down eventually to 0. And so anytime you can differentiate down to 0, like for example on this next one, what's the derivative of x squared?
2x.
2x,
And then the derivative of that,
2.
and then the derivative of that,
0.
0. Anytime we can differentiate down to 0, we should be able to follow the same pattern of function times integral minus next derivative times next integral plus next derivative times next integral minus next derivative times next integral, just by flipping signs. And so what is the integral of sine x?
Negative cosine x.
So these ones we're going to use integrals, and we're going to get negative cosine x. And what's the integral of that?
Negative sine x.
And what's the integral of that?
Cosine x.
So we've differentiated and we've integrated each time. Okay. And what we're going to do is we're going to group it this way. Original thing that we took the derivative of gets grouped with the first integral. Oops. Then that one has a, that one is a positive thing. It ended up being a negative because one of our integrals was a negative. But then the next one will become a minus, and it will be this one times this one. So this becomes minus negative 2x sine x. And then the next one, since that one was a minus, the next one should become a plus. Plus our constant. And so this, using this sort of shorthand notation, which ends up giving us negative, x squared cosine x plus 2x sine x plus 2 cosine x plus our constant, can be a lot easier if one of them differentiates down to 0 and the other one can be integrated repeatedly as many times as we need to get the derivative to the other one 0. This method is called tabular integration, and it's just a shorthand notation for integration by parts with this special case. Good or no?
Does one need to be repeatedly like differentiable forever, or can it just be repeatedly differentiable enough times for the other one to equal 0? I mean, integration.
Yeah, it doesn't have to be repeatedly integrable forever. It just has to be, I have to be able to integrate it as many times as it takes to get the derivative of the other one to 0. So this one was 1, 2, 3 times. I got to be able to, fairly easily integrate this 3 times.
Okay.
Same thing here. I would have needed to take, 4 derivatives here, 3x squared, 6x, 6, 0. So I'd have to be able to take 4 antiderivatives of e to the x, which obviously each one of those is just e to the x. But good or no? We're going to do a couple more like this. I just want to set that up. Are we okay with that or no?
Yep.
Hopefully. All right, let's take a look at this next one. 2x cubed plus 3x squared minus 2x plus 1 times e to the 3x. If I repeatedly take derivatives of one of these, will I eventually get to 0?
Yes.
Yes. The one on the left, right? What's the first derivative? Should be 6x squared plus 6x minus 2. And what's the first integral of e to the 3x?
1/3 e to the 3x.
1/3 e to the 3x. And then here, next derivative should be 12x plus 6. And next integral should be 1 over
9.
9 e to the 3x. Next derivative should be 12. Next antiderivative should be 1/27 e to the 3x. And next derivative should be 0. And next antiderivative should be 1/81 e to the 3x. Good or no?
Good.
All right, so we're going to combine original of the one I took the derivative with first one I took the integral of, and those will be combined with a plus. These two will go together with a minus, these two will go together with a plus, and these two will go together with a minus. And obviously we don't use the 0 because 0 times the next one would be 0. So our final answer here should be, this is going to be 2x cubed plus 3x squared minus 2x plus 1 over 3 e to the 3x, right? There's my 1/3 e to the 3x, and then that first term. And then minus 6x squared plus 6x minus 2 over 9 e to the 3x plus, I could, if I wanted to, divide a 3 out of this, but I'm not going to bother. 12x plus 6 over 27 e to the 3x, and then plus 12 over, or sorry, not plus, minus 12 over 81 e to the 3x plus the constant. And obviously there's a little bit of simplification you could do, right? This could become, if you divide a 3 out of that, that could become 4x plus 2 over 9. And this one, if I wanted to, I could make that 4 over 27, but not necessary. Good or no? That is tabular integration. It's a shorthand for integration by parts. Good or not good?
Good.
All right, we're going to do one last problem today, and then we will be done. I'll give you guys a second to do this one on your own. You should be able to use which type of integration here?
Tabular integration.
Should be able to use tabular integration. So I'll give you, I don't know, 2 minutes to do it. We'll make sure you guys all got it right, and then we'll be good. Ready, go. So we took our derivatives of 2x squared plus 3x to get 4x plus 3, followed by 4, followed by 0. And we took an integral of cosine to get sine, an integral of sine to get negative cosine, and an integral of negative cosine to get negative sine. So we attach the 2x squared plus 3x with the sine x. Minus the 4x plus 3 times the cosine x. And then it's times another negative, so plus. All right, and then, we do this one with a minus being multiplied into between them. And then this one we do with a plus between them, so that should become minus 4 sine x, and then plus your constant. Good or no?
Good.
All right, that's the basics of integration by parts, along with the shorthand tabular integration method. Note that sometimes when we integrate by parts, it works out real nicely with 1 or 2 applications of it. Sometimes we have to go through and we end up with the same thing that we started with, and we've got to go back and resolve for that thing that we started with. So just recognize when you end up with an integral within your integration by parts that is identical to the one you started with and what you need to do with it then. Okay, so I got a question that if that was a definite integral, how would we evaluate it for the last one we were just doing? Yeah. Yeah, so just if, if I said this was from 0 to 1 or whatever, we just go in and at the end plug in 1 for everything and subtract, plugging in 0 for everything, and just get an answer from it. Yeah, I would just do the tabular integration first and then just plug in the values. Yeah, sometimes with the when we do where's that inverse tangent one that we did? Here it is. So sometimes when we do the integration by parts on a definite integral, it gets a little bit confusing to people because you end up with like this thing already that we need to evaluate, and then with another integral that has the same limits, and then you might end up changing the limits. But you can always just integrate the original function, inverse tangent x, get it all back in terms of x, like we did here, and then evaluate this from 0 to 1 in the very end. So there's no real difference between an indefinite or a definite integral for the integration by parts. Any other questions? All right, that's it.